Okay. Good morning. So let's go to 24th lecture. So today I'm going to talk about Hodge locus. So I don't know if the version of Hodge locus and Hodge theory that I'm presenting is more understandable than the other versions in the books, but anyway, that's at least I tried. Okay, so let's go. So first, let's talk about cohomology bundle. Cohomology bundle. So I will introduce Hodge locus in a more general context, but then I will go to Fermat and hypersurfaces, which is a special case. So let's xt smooth family of projective varieties. So okay, so by Ehrenmann's vibration theorem, Ehrenmann's vibration theorem. So if let's say the fibers, let us denote with xt. Let's say here xt, the fiber over t. So all these xt1, if we took local open sets, t1, t2, this is a small open set inside t. Then these are C-infinitely the same. And in particular, this will give me isomorphism in the cohomologies. H star x t2 z, and this isomorphism is unique. This is not unique, but any two of such isomorphism are homotopic, so this will induce unique isomorphism. And at the end of the day, okay, so let me, so I will, why I need this one? I need this one in order to say that this cohomology bundle. So let's say, let's fix dimension for the cohomology. Let's say M, HM. So HM XTC. T in T. So let's since I'm okay. So the idea is that I want to show that this is a fiber bundle, and but the point why it's a fiber bundle, because for any T I have this all these vector spaces which are of the same dimension and so on. But this is just the intuition of our fiber bundle. We have to furnish charts for this bundle. So what this will imply that HM is really a fiber bundle, and the reason is that maybe just I explain it in picture. This will give this unique isomorphism will give us a trivialization. So maybe just making the picture. So here let's say T. Here I have HM XTC, and from another side what I have here, let's write it here, HM XTC is inside, it's inside, I have this lattice HMXTZ. And from now on, I will forget torsions, and all the cohomology that I'm considering are up to torsions, so I don't care about torsions. So at the end, what this is a lattice, a kind of lattice inside this C vector space. And these isomorphisms are unique. This means that at the end, let me say, so there is let me if let's put this one T0, because to use T for arbitrary, so and arbitrary point, let's call it T. If we fix let's say V1, V2, VB, HM, XT, 0Z, there are unique okay, so and so if we fix this one and then we do monodromy, so this monodromy is exactly this the image of this VI's under this isomorphism. So V1T, V2T, VBT, the monodromy of V1. So let's call this one T0. Maybe I'm a little bit. So we fix V1 T0, VB T0 here, and then we make it monodromy to arbitrary points. So these are a basis of H. If we fix a basis, this is a basis HMXT Z. Monodromy of V1 T0, blah blah blah, V1 VB T0. Then the other moral of the story is that they will this V1 T and VB T as a function, let's say as a function in T, let's put a bullet, as a function from U to H, will give us the trivialization of H in U. Anyway, but this is just a detail that you sit down and you observe. We can also proceed with this, just this, let's say, the most primitive version of a cohomology bundle, such that over any point we have a vector space of the same dimension. But if you want to write in charts, you have to consider all this fixing a basis, doing monodromy, and so on. Anyway, and by this construction, this is actually, this is actually holomorphic vector bundle. And even so, if we start from we have already started with the algebraic family, this is actually algebraic. So for the moment, I will not bother myself with all these details, but slowly we will get used to this. Holomorphicity is already clear from this argument, but algebraicity it's not yet clear. And yeah, okay. So we have this cohomology bundle, and from this cohomology bundle also we have Hodge filtration, let's say, bundle. So let's say let me call this HM, and it is natural to see what is HMM. So we will have F0, F1, and then fm plus 1 equal to 0. So fi at the fiber of fi at t, it is just fi, the piece of the cohomology hm. Let's for the moment use the usual, not the wrong cohomology, xt what c, which is the same. This is the same as fi hm the Rham xt. And again, it is I don't know if it will help so much for our computational purpose. This is again one can see that it's a holomorphic bundles. And if one use this algebraic de Rham cohomology version of Hodge filtration, then actually they're algebraic bundles. But in examples, you will see that these things are automatic. Even you don't need to prove the things. Okay, so this is the so just something that you carry in mind. Maybe let's maybe this picture will be, you have this parameter space T over T. You have of course you have your variety xt, but your variety is xt is something non-linear. You substitute it with its cohomology. Let's use the Rham cohomology because at the end I will use differential forms. And this guy has sub bundles f0 t, f1 t, and so on. So we have these sub bundles. Another structure also that we have this lattice hm xtz inside hm the Rham xt. And once again, my cohomology with z coefficients are up to torsions. I have neglected here the torsions. Okay, so knowing these things, now we can define what is a Hodge locus. So let's define Hodge locus. So let for this one. So basically, what is Hodge locus? I mean, you take a Hodge cycle and you want to deform it to nearby fibers such that still it is Hodge. Okay, so for the Hodge locus we start. We start from Hodge cycles. For my t, I will has always a point called 0. This is a kind of I mean just fixing a point in t or fixing x0. Okay. Delta. So let's take hm x0 z Hodge cycle. And intuitionally, what is Hodge locus? In a moment, I will define. So this is the intuitional definition. So this is just as I said, this is just t in t in. Let's put t here, 0 here. Maybe let's it will be at a local object. So at the end, let you take a small neighborhood of 0 in t, and at the end I will also use this notation t0. This means that a small neighborhood of 0 in t. So it will be some all t in t0 such that delta t is Hodge. So what is delta t? Delta t is the monodromy of delta 0 2 to HM xt z. So remember that so, and this monodrome, it doesn't matter along which path, because this small set is simply connected. Any path from 0 to t, any two paths will be homotope to each other, and so the passing to homology, the monodromy will be unique. Anyway, the point is that topologically, we can transfer delta 0 to nearby fibers without any restriction. But once I say that, okay, I am interested on Hodge cycles, so delta must be a Hodge cycle also, then I get some restrictions. So this means that I can define this set. So for the moment, it is just a set, but now we are going to make a rigorous definition. This was a kind of intuitional definition, such that it becomes some analytic set. So let's go. In order to make a better definition of the Hodge locus, so we have to return back to the definition of Hodge cycle. So omega 1, omega 2, omega 3, omega, let's say, S, sections. So I need this Hodge filtration sections of f n half plus 1 of hm. Let's say local holomorphic section. Local holomorphic section, such that at any point, let's say t in small neighborhood of 0, so at the local holomorphic, so these are sections of in this small neighborhood. I called it also U, such that for any point they form a basis of the fiber f n half plus 1 h. So the fiber is this one, xt up there. Anyway, in order to make a rigorous definition of Hodge locus, then I have to take I will take sections of this guy, which at point basically I will take basis of these pieces. And once this is done, then we know what is the definition of our Hodge cycle. So delta is Hodge if and only if omega I delta t is equal to 0. So the basis I equal to 1, 2 until s. And okay, so this is just by definition of our Hodge cycle. But something now we have to see what it is these guys. Now, in order to make this better definition of the Hodge locus, omega I. So omega i's are holomorphic sections. They are holomorphic functions in this T0. So I have a bunch of holomorphic functions. So in a neighborhood of 0 in T, and so this is the point. These now we are out of algebraic geometry framework. These are not at all. These are just some transcendental numbers, functions. And so let's let's say a ring of holomorphic functions in T0. Let's this one denoted by O T0. So this is not the algebraic structural sheaf of T. Otherwise, for now, I am using it as the holomorphic structural sheaf of T. So this will be the ring of holomorphic function in a neighborhood of 0. So it turns out that we have these guys here. So all these guys are here. They belong to here, and of course they will form an ideal. Ideal omega 1 delta T omega S delta T. By the way, this S is what? This is, let's write in terms of Hodge number. This is H and, just a moment, I have made a mixture of, I have not mixed N with M. No, it is so. Oh, sorry. Then I have mixed N with M. So this is M, because I am doing in general. N for me will be always the dimension. So let's say M. So for the moment there is no N. N is the dimension of X, and in the hypersurface case, N will be the same as M. But in general, I will use M for some number between 0 and 2n, n-dimensional. Okay, so this is hm0 plus hm minus 1, 1, plus these are Hodge numbers until hm half plus 1, hm half minus 1. Anyway, what we get this ideal inside holomorphic ideal inside T0, and well, Hodge locus is just a zero set of this ideal, because when something is for T is this 0, then we have this Hodge locus. Okay, so it is now Hodge locus is a little bit more concrete. It is the zero set of this ideal, but actually I will maybe I go a little bit to this revolution in algebraic geometry by Grothendieck. So first, sometimes the ideal itself is more important than the zero set, because the ideal contains more data. So first of all, we don't know about this ideal, if it is reduced or non-reduced, if it has nilpotent, it doesn't have nilpotent. So we don't have any idea about if this ideal is good or not. So at the end of the day, they are just saying that the zero set of this ideal, we just are interested in this the geometry. But the point is that this ideal itself will contain more data. That's the reason that Hodge locus for us will be the analytic scheme. So in some sense, it will be just, let's call it this V delta, or let's say V delta 0. So this is analytic scheme. So, okay, it is, in order to find it as a scheme, then it must have the ring of function. So if we have to define its ring of function, its ring of functions, it is just O holomorphic functions quotiented by this idea. So so you see that now it is not just a geometric object. It is some half. It's also, it has a scheme structure object, and the reason is that this object is something finer. For example, it might happen that Fn belongs to this guy. Let's call this one O, ring of function of O V delta 0. It might happen that we have f v delta 0, but it has nilpotent, but f doesn't belong. So this ideal can be as bad as any other ideal in algebraic, in computative algebra. And there is a reason why we will consider this one, because we will get some information of the tangent space of this scheme. Okay, let me. No question. Okay, so this is the general context. So let's return back to our special case. So let's go back to hypersurface. Again, in the case of hypersurfaces, I am not really interested in arbitrary hypersurface. The point is that I invested a lot to talk about Fermat varieties. So the idea is that I want to look Hodge locus passing through Fermat variety. So remember that this we look to equal to 0, and then we projectivize it and so on. But now I will consider any arbitrary hypersurface as a perturbation of this guy. So let's say Tj. Now I will use this notation xj. Let's say G. Let's define what else. So basically here, what I will take, this is all monomials in x0, x1, xn plus 1 of degree d, because I want a smooth hypersurface of degree d. So I will take as much as parameters for any monomial, and and actually for let's say g. Let me call it. Let me see what I want to say. Well, if you want the space of all hypersurfaces of the same degree, then this is this one. But for our purposes, it turns out that we can a little bit cut out some monomials. Let me say which monomials we can cut out. So let's say our G0, x1, G1, xn plus 1, gn plus 1. It turns out that for our study of a Hodge locus, we can reduce this number of monomials by just considering this gi between t minus 2 and 0. And well, for the moment, just consider let's just this deformation of the Fermat variety, but this will not be a big restriction. Anyway, with this class of monomials, also we can capture the Hodge locus and its properties. Anyway, so the general context is all monomials, but I will take this ID, this set of this indices G0, G1, such that GIs are between 0 and d minus 1. Anyway, you see that here I have my T. My T is basically it is C to the number of this ID. I have my 0 in T, which correspond to Fermat, because when I put all tj's equal to 0, I have the Fermat variety. And what else? Yeah. So I will focus from now on to the Hodge locus passing through Fermat variety and for hypersurfaces. Okay, so let's see what. Okay. Now I need to choose a sections of the cohomology bundle, and for this one we have to, because I want to study the Hodge locus, and we have for this one we have to return to. Griffiths' theorem. So maybe let's write in this one as proposition. Okay, let me introduce few notation. Oh, before going to this, I have to restriction to affine variety. No, let's write first the proposition and then restrict to the affine chart. So here we have projectivization of this one. Okay. Okay, so let's maybe one notation. Maybe this polynomial, let's me call it ft. So f0 is the Fermat polynomial. Proposition: if this xi xi is if this collection of monomials, let's say, if you have a collection of monomials, let's say this is a collection of monomials. For the moment, I don't introduce the index set. Form a basis for. So the Jacobian, remember that for the Cx divided by the Jacobian of f0. See this? Well, actually, in the Fermat case, I can write down explicitly. Let me see. Let me see what I am going to do. Okay, let me for the moment ignore whatever I wrote it here. Let me remember this I0 x1 I1. So that's xi x and plus 1 I and plus 1. So these guys, I0 plus I1 plus I2, In plus 1 equal to, let's say, dk minus n plus 2. Maybe I write and then I explain. K varying between 1, 2 until n. Let me see which n plus 1, and all i's k's are between d minus 2 . So let me see. I want to fix the basis of the Jacobian ring. Maybe okay. So let's take these ones. Maybe okay. I'm making a little bit. So let's take this one. No, actually it was okay. Ik between d minus 2 is 0, and Yeah, okay. I was. Let's write the same thing that I had written before. That's sem I k is k d minus n plus 2. Okay. So first of all, they form. This is a basis. Is a basis of Jacobian ring divided by Jacobian of the ring of polynomials in X divided by Jacobian of F0. The Jacobian F0 is just very simple. This is X0 to the D minus 1. So what I want to say that is they form the basis of this guy, KD. So here for K fixed. So here for K equal to 1, 2 until n plus 1. This is just a very since f0 is just this polynomial, we can you see that so xi to the d minus 1 is already 0 here. So trivially this will form a basis of this guy. And remember that why we need a basis of these things, because maybe I say this one, where is the other? The point is that from this one, we constructed the Griffiths basis. So xi, remember there was this omega, then divided by f to the k. This will induce, to the projector, this will induce elements in Hn plus 1, the Rham Pn plus 1 minus x0, let's say everything is 0, and then yeah. For the construction of the the elements of the cohomology of this complement, which is basically the cohomology of x0, then we start with fixing this monomial. Anyway, what I want to do, I want to introduce I want to take sections of the cohomology bundle, and the reason that I'm recalling this one, because if we fix actually any basis of these pieces of the Jacobian ring, then at some point 0, so let me see, everything is 0, then it will be a basis also in some neighborhood of 0. So the same, so the same xi will be also a basis of Cx. Now Jacobian of ft, let's say the homogeneous piece, what was the homogeneous piece? dk minus n plus 2 for t in a small neighborhood of 0 in t. So this is small neighborhood now, I can explain it easily to the usual topology, analytic topology. So here t, so this will be small in the usual sense, but actually this one can also take the one can take also Zariski neighborhood in t, because t is also itself is an algebraic. So this one I will not explain, but the small neighborhood, it is it follows again this the fact that the let me see, um, Maybe one reason why or this is small neighborhood it follows because from this remember that from these xi's we construct these cohomology sections. Okay, so the reason is this one. So we have already seen that our zero, we have a cohomology, we have the cohomology bundle, and basically it's if we choose a basis, our one fiber. So just imagine that our zero, we choose a basis, and at the end of the day, these are holomorphic sections of the cohomology bundle, such that at point 0 they form a basis. And then if you have sections of a holomorphic bundle such that at a point they form a basis, they form also a basis. They form also a basis in a in T in a neighborhood of 0. So this is a basic fact in holomorphic vector bundles, or even in C infinity, that if you take sections of a vector bundle such that at one point they form a basis, then in a neighborhood of that point also they will form a basis. So this means that at the end we take our cohomology bundle and our sections of the cohomology bundle. Anyway, so the moral of the story is that in order to play with the Hodge locus in the framework of hypersurfaces, we just need to handle these differential forms. Okay, so let's go. Any question? Let me see how many minutes I have. So the main theorem, let me see what matrix pi plus J. Okay, so again, I will restriction to the affine chart. So this x0 equal to 1, because as I said, we are looking for Hodge cycles and so on, and in the notion of we want to write them as vanishing in terms of vanishing cycles, and that then these things are in the affine chart. Okay, so this means that at the end when I put here there, then let me write it in this way. So it will be 1 plus x0 x1d, maybe the one that I have written already in the book. So so here we'll get 1 plus, let me write. So by this transformation, x0 going to zeta 2d x0, we can transform this 1 into -1. And the reason is that this equal to 0, I described the vanishing cycles and so on, but at the end you can also put arbitrary s here. But for the moment, just let's take this one, and then t j x to the j, and what is that? So I have to rewrite my notation in terms of in the affine chart. So this notation now, this id is the same idea as before. So, but cutting the contribution of x0. Maybe I will write here. So ID for me will be. So remember that I was 0, 1, 2, d minus 2 on n plus 1. So ID in this case will be, I am just projecting it to x1, xn plus 1 coordinate. So it will be I in I such that, now I will use also my A beta notation. Remember this, my I notation. Usually I put beta, use also beta. So this will be 1 plus strictly bet 1. So let me see, k equals to n plus 2d, and then 2d. And okay, so for the notation of the Hodge pieces also, I will need these guys. So let's say, let me also define also. These are just notations that I, after translation to the affine chart, I am using it. This is G in I, such that AG. Let me. Okay, let's see. Could be the same I. I don't know. I. But
Hossein, just a question.
okay.
What is exactly your goal here? You know, like what do you want to compute now?
No, the main I am going to compute the tangent space of the Hodge locus, because and then I will tell the applications why this tangent space of computing tangent space of the Hodge locus is useful for verifying something called infinitesimal Hodge conjecture. I'm preparing to study the Hodge locus passing through Fermat, and in order to, this is the integrals are complicated, so I want to compute its tangent space.
Okay. Now I see.
So I'm preparing the old notation to compute the tangent space. So I just a moment, I will now. Anyway, okay. Let me fix this and also let me write. Okay. Anyway, what I'm saying now, this deformation of the Fermat variety that you see here is just the previous deformation that I wrote in the previous page, but I restricted to affine variety. So the previous ID, when you neglect this this I0 coordinate, then you will get this one. It is remember that the monomials of degree d and the power of each xi was between 0 and d minus 2. And okay, so now that Felipe asked, now I have a kind of good understanding of the Hodge cycle here. Even so, I don't know nothing about Hodge conjecture. Well, for now I have not told something about Hodge conjecture for Fermat variety. The idea is that I want to study Hodge cycles in when I am deforming it, and this has produced the notion of the Hodge locus. And the next step, I want to compute the tangent space of the Hodge locus. And then I will say why the tangent space, the computing the tangent space of the Hodge locus will be useful in order to understand the Hodge conjecture. But for now, the main idea is that Hodge cycles are something like are very rare stuff. If I know that they come from algebraic cycles, of course there are many examples. But finding Hodge cycles that you don't know their origin, if they're algebraic or not, it's difficult. And I want to a little bit understand these Hodge cycles and understand their deformation. When I want to understand the deformation of some object, this means that I have to understand also its first order approximation of the deformation, which is the tangent space. So all these things is for this one. Okay, maybe I introduce the main theorem that I want to prove next time, and then we finish it. So so let's so this one, remember that this one remember that so let's take this delta 0 h n x0 z Hodge, and let's assume that it is supported in the affine part, so we'll call the primitive. So in the last lecture, what I told, this is exactly the middle part. I mean, omega I, when we construct it from these guys, this is the middle part of the Hodge decomposition where the periods might be non-zero. So these pi, so for example, if I form this pi just using this differential, these are automatically zero because of the definition of the Hodge cycle. So this is Hodge cycle. And okay. I will define a matrix. I will just prepare the ground, this pi plus g, I in ed, g in n half plus 1 and half minus 1. Anyway, first I will define a matrix whose rows are indexed by id and whose columns are indexed by this one. So for I in id and g here, I have to attach a number. So it is not a usual matrix indexed by 1, 2, 3 until k, and then so it is a matrix indexed by this finite set. So in the ig, so this is in the ig entry, what we have, it is pa plus. So if you do this I plus g, this is just the usual sum of two vectors, then you will land on this index set. And once you land in this, then you can make the integration this integration, and you can define pi plus g. So next time I will show the, well, let's say, implementation of this matrix in computer. But let's for the moment just introduce the main theorem. Which is theorem 16 point in my book. So next lecture I will try to prove this one. The Zariski tangent space of Hodge locus v delta 0. So I have fixed the Hodge cycles in the Fermat variety can be identified is canonically isomorphic to let's say kernel of this pi plus g matrix, pi plus g. So this is a matrix, and what the kernel, this will be v in c id such that ti plus g v equal to 0. This is my goal. So is that the Zariski tangent space of the Hodge locus, it is computable. And what it is, first, I form this matrix. Remember that these P's were periods of the Hodge cycle that I can compute it explicitly. And then this was the number of rows of this matrix, and at the end, the kernel of this matrix is the tangent space. And in particular, what we can, well, this is a kind of typical in algebraic geometry. Sometimes when we want to get some information about some algebraic variety, if first we try to understand its tangent space, and after and in this case, I don't have algebraic variety. By Deligne-Catani-Kaplan theorem, which is another story, these are parts of algebraic varieties, but for now it is not algebraic, it is just analytic. And so this we have this formula for the tangent space. The classical presentation of the tangent space of Hodge locus, if you go to the works of Griffiths or Voisin's book, at the end you have to go through this infinitesimal variation Hodge structure and so on. But the idea is that in the case of hypersurfaces, it is just some integral manipulations. So maybe let's do in this way. So the next lecture, I will remind a little bit some notations around this theorem, and then I will try to prove this one. And something else also, that the Zariski tangent space of V delta 0 as a scheme and not just as a set. This is a very important fact. Maybe I as an analytic scheme. Take a scheme. Okay, maybe some. Let me give some examples such that let's okay. Well, for example, CT. Let's to say that the Zariski tangent space of the variety as the usual variety and the scheme might be different. Maybe let's take a line A1 A1, let's say T point, and let me, I am not prepared, but let's try to write it. Okay. Maybe if I make you. So here we have two schemes. Okay. So what are the tangent spaces at t equal to 0 of okay, the Felipe or Mateus, if you have done
the second one is just a point, right?
That is the point. So this is in this case it's just 0, no, the tangent space,
Yeah.
because it is your point. But if what is it in this case? In this case, it is the whole space actually.
Yeah. It's linear, right?
It is linear. The dimension. Well, let's write the dimension. Dimension. Here is 1. It is 0. And you see that when the tangent space of a scheme is different from here, it just represents the variety t equal to 0, which is a point. But here we have the scheme structure, and you see that the tangent space is different. Here the one dimensional, here 0 dimensional. In the same way, I mean, the only thing that we have done, we have used holomorphic functions. Here I have used algebraic, but here, in order to find this one, I have used holomorphic function. And so, so just carrying this one as an example in mind. And what we are going to compute here is the tangent space of the scheme and not the variety. So you see that the tangent space of a scheme might be bigger than the tangent space of the underlying variety. This is the moral of the story that you want that I want that you keep in mind. And